This is a total production. Hello, Chem Minions. Welcome back. So to Elementary Organic, this will be Chapter 4 where we talk about chirality. So one of the things you need to be able to do is look at a molecule and recognize whether it's chiral. So I chose some chains and some rings and some combo rings for us to kind of look at and figure out. So one of the big takeaways here, if you're going to identify, we're going to focus on chiral carbons. All right, and so if you're going to have a carbon that is a chiral center, the easiest thing to remember is it's got to have 4 different groups on it. All right, the groups have to be different, meaning would we name them something different? So for instance, if we look at this first structure here, when we look at it, you've got a 2 carbon group coming off of it, and then another 2 carbon group. So even though I gave you a dash here, that doesn't mean this carbon is a chiral center. So this carbon is what we would call, this molecule is a chiral, right? Specifically because it does not have a chiral center, right? So this is not a chiral molecule, it's a chiral. All right, next up when we look, having this dash here, that's kind of we need to pay attention to it. So does it have 4 different groups? Well, it's got a chlorine, it's got a methyl, and it's got an ethyl group. So those are 3, and then we know by process of elimination that there is a 4th hidden group because we don't ever show carbon-hydrogen bonds really. So in this case, we know it has 4 different groups. So that right there is the chiral center. All right. And so just to also let you know, I put a wedge on the hydrogen strictly because every carbon that has 4 bonds is tetrahedral. And so if it's tetrahedral, right, it doesn't just have 4 bonds that are in plane like that. It always has 2 that are in plane, 1 that's a dash, and 1 that is a wedge. All right, that's what's most important there. Okay, so you're always going to see on a tetrahedral carbon those 4 bonds, 2 in plane, 1 dash, 1 wedge. All right, and so here when we look at the wedge OH here, we see we've got a methyl group, an OH group. We've got this isopropyl group, right? This whole thing is isopropyl. And so that's 3. And then we know that there is a 4th hidden hydrogen there. So that is definitely a chiral center. Now, if we look at this one with the dash, that's a methyl and that's a methyl. So there aren't 4 different groups on it. So this only has 1 chiral center. All right, I'm trying to show you how tricky I can be at times. All right, next up we have this dashed NH2 group. So there's a methyl group, there's an ethyl with an NH2, there's the NH2, and then there's an understood wedged hydrogen. So that's definitely a chiral center. And then same here, you got an NH2, a methyl, an ethyl group with an NH2, so that's also a chiral center. So that one has 2. And the interesting thing about this one, sorry, I didn't show you the understood wedged hydrogen, but the interesting thing about this one is this, even though this has 2 chiral centers, this compound has a plane of symmetry right here in the middle, right between those 2 chiral centers. And this compound is what we would call a meso compound. All right, so meaning, even though it has chiral centers, this molecule is actually achiral. It shows no optical activity. So meso is pretty much the same as also being achiral. There's a lot of different situations to be achiral. All right, next up we have a wedged ethyl here. So when we look, that's an ethyl group, that's a methyl, and that's a 1, 2, 3, 4 carbon with a bromine. So that's definitely unique as well. So there's 3 different groups there, and we know, or that it's understood, that there's also a dashed hydrogen. So that is definitely a chiral center. Now we look where the wedge on the bromine is here. There's only 2 things shown, so that should be a dead giveaway. That if there's only 2 things shown, that means there's 2 invisible hydrogens. So because of that, this is not a chiral center. And let me try and turn that autofocus off so it'll stop doing that. It's still doing it. I really wish you would stop. All right, it's still sort of doing it. For some reason, I can't get it to stop. All right, next up we have a ring and we have a wedged hydroxyl group. Now in rings, if one of your carbons of the ring is suspected to be a chiral center, you want to cut through that ring, through that carbon of the ring. So what I'm saying cut, I want to cut right here. And I want to investigate the two different sides of the ring specifically on either side. So we have this group and this group. Those look like a mirror image of one another. So this doesn't have 4 different groups. It really only has 3 different groups because of the symmetry that you see on either side here. So this would be another achiral molecule because it doesn't have any chiral centers. Next up, same thing again, we have a wedged OH group here. And so if I were to cut, well, I didn't do it a perfect job, but if I were to cut it in the middle along that, through the middle of that suspected chiral center, I see that this side and this side are the same again. So this is yet again achiral. Okay. Now I see another wedged OH group here, and I suspect this is a chiral center. So when I cut this, you notice now I have a double bond on this side, but I don't on that. So these two sides are different, and with the understood dashed OH, the dashed hydrogen there, that's definitely a chiral center. So we finally got one. We look here, we've got an understood dashed hydrogen. I'm going to cut through the middle here, right? And so the left and the right sides of the ring don't look the same, right? The pi bond's over here, but not over there. So this has 4 different groups. So that is also a chiral center. We look here. I'm actually going to have to do 2 cuts. So when I cut here, right, the sides of the ring are definitely different, right? Because I got an OH on this side of the ring, but I don't on that. And there's an understood hydrogen. So 1, 2, 3, 4. That has 4 different groups. Therefore, that's a chiral center. And if I do the same thing to this one here where I cut it there, I know, so I'm cutting along this line right here. I see that this side and this side are different, right? This side has the OH up there and this side does not. And there's also that understood hydrogen. And so with that, this is also yet again another chiral center. It's got 4 different groups on that carbon. All right, now let's see. Another interesting thing about this compound, I'm going to redraw it. So let me come down here and redraw it real quick. OH, OH. So this is another example of one of those. Come on, zoom. This is another example of one of those meso compounds. This has a plane of symmetry right between these 2 chiral centers. Right, so to be meso, you have to have chiral centers first, and you also have to have a plane of symmetry that goes right in between those 2 chiral centers. So here, this plane of symmetry makes this meso. So even though it did have 2 chiral centers up there, this is a meso/achiral compound. It doesn't show any optical activity. All right, next up, we've got this 6-membered ring that's got chlorines and a fluorine. All right, so when we look, at the dash, and the wedge there, if I were to cut right here, this side and this side of the ring are different. So, and there's an understood hydrogen there that's wedged. So I would say, yes, that's a chiral center. And if I were to do the same thing to this one right here, this side of the, so going along that line, right, this side of the ring and that side of the ring are different, right, because it's a chlorine and it's a fluorine. And there's also an understood wedged hydrogen there as well. So that's a chiral center. Now, if you were to do the same thing with this fluorine, though, this side and this side are exactly the same. So this is not a chiral center. So this only has 2 chiral centers. And this is another example like this, where this is actually another meso compound, because you have this plane of symmetry in between these 2 chiral centers where the chlorines are. So this is also meso. I'm going to put meso under that one as well. Okay. Now, if we look at this one, so it has 2 chiral centers, but it's achiral because it's meso. Now, if we look at this one, this still has that same plane of symmetry here, right? So that is still not a chiral center. Even though this is wedged and this is dashed, it still has the bonding the same, CH2, CHCl, CH2, CHCl. So you can assign different priorities to these, okay? So this is still not a chiral center, but this carbon and this carbon are still chiral centers, and now this is no longer meso because the chlorine is dashed and the chlorine is wedged, so there isn't a perfect plane of symmetry, right? So this plane of symmetry is artificial. I really just did it to show how the stuff on this side is the same as the stuff. Like the stereochemistry is not the same, but the stuff that's there, CH2, CHCl, CH2, CHCl, those are the same. Okay, so now this has two chiral centers, and it's not meso. It is a chiral. It is chiral. Okay, optically active, aka. All right. Here, this one wants us. We don't have stereochemistry on these. I really just wanted you to find the carbons that have 4 different things on them. And so, if you were to look, all of these on the outside of the rings, those are definitely no, right? They all have 2 hydrogens. But if you were to look here, 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 and here, are there any plane of symmetries we could draw? Could we draw one here or here? If we try to draw planes of symmetry through these 2 carbons, we don't get stuff on the same side. So this carbon and this carbon are definitely chiral centers. We look at this one, right? If I cut it here, this side and that side wouldn't look the same. So that's also a chiral center. However, when we look at this one, it cuts perfectly. So oh wait, no, you have that methyl group there. So because of this methyl group, these 2 sides aren't the same. So this has 4 chiral centers. All right, we look at this one. Everything on the outsides here, 1, 2, 3, 4, 5, 6, 7, 8, those are definitely having 2 hydrogens apiece. So we don't look at those. But if we look at this one and this one, right, we can cut them both right here, and this side look the same. So there is 0 chiral centers in this molecule. So I'm just going to call this one achiral, right? No optical activity. Now though, there's one alteration to that ring, right? If I still try to cut right here, now the two sides don't look the same. And so I would call this and this chiral centers, right? And now that this has a CHO group on it, we also know that there's a hydrogen that's invisible. So this now has 4 different things on it, and that's a chiral center. All right, so hopefully this kind of helped you in trying to identify chiral centers, specifically chiral carbons. Anyway, so in the next video, we'll actually look at assigning configurations that are R or S, what we call absolute configurations. So anyway, until next time, stay weird.